Okay, let's dig into an example. So this is a fairly simple example, one-dimensional deformation of a bar. So here is the outline of my bar, its original shape. It's constrained on the left. It has a length L, and I want to illustrate this point by talking about 2 points. So imagine that you draw 2 dots on this bar at point A and point B, and this has a length of delta S. Then we're going to apply a force F, and we're going to stretch this bar out to this location. So we're defining my displacement at the tip of the bar from that point out, and that displacement is u of x. So I've got a coordinate x here. So when this is stretched, this point moves to this x at A bar, and this point moves to x at B bar. So the relative change in this element is delta S prime. So from your Mechanics 1 course or whatever undergrad course you took, we define an average strain over this finite distance. So it's my displacement U over L. And we can also represent that by delta S prime minus delta S over the original delta S. So this is an average over this this entire element, okay? And my U is defined from here to here. So the strain at a point is found by taking the limit on delta S. So we shrink this down until these points are very close to each other. And what you get is a derivative du over dx. Well, in the finite element problem, what we do is we don't take this limit all the way to 0. As I mentioned before, if I come briefly back up to here, we're talking about finding displacements at discrete points. So these will have finite lengths, okay? So we interpolate between those points. So as you go over x, we have these 2 unknowns, a and b. So this is my interpolation function for a 1D problem. It's not the only interpolation function you could use. You could use higher order quadratic. You could use other types of functions. We're typically going to use polynomials in this class, and I'll show you later in how we choose what order of our polynomial. In this case, we're only interested, or primarily interested in strain, so we take a derivative on u with respect to x, and we get this constant b. And that's sufficient for this problem. If we stretch this, my strain will be uniform everywhere. So that's all we need. We're going to have a constant strain, and it's just defined by b. A is can be set to 0, or it can be set to some finite value. It's a relative rigid body displacement. Alright, let's talk about a more complex case. So the previous case you can do by hand. The difficult problems that we end up using finite element for is for more complex stress states. For example, let's say you have a cone like this. You put a load P on it. This comes down, touches an elastic solid that's constrained on the bottom, and as P increases, you introduce a stress concentration. So these lines correspond to some change in the internal stress. Well, when we solve this with a finite element problem, remember I said we have to interpolate between points. So you get solutions at these discrete points. Well, if you have very large changes in your stress as you move away from this point, you need to resolve those differences here. So there'll be larger gradients. Alright? If you come back here, the gradient is 0. strain is the same everywhere. Here your strain is very large here, and then it drops off, and eventually way down away from the concentration here, strain is constant. So one of the things that we'll have to carefully look at in this class is if you have stress concentrations or field concentrations or any change in your solution with respect to space, you have to be very careful in how you construct these elements. The nice thing is, as you refine your mesh, if you continue refining it, this will converge to the correct solution if it's linear. Nonlinear problems are a different story we'll get into later, but this method will converge to the correct solution. So if you were to continue refining your mesh, this should converge to some analytic solution if it exists. So here's a few examples that you can use finite element for. And basically, if you can construct a PDE, a partial differential equation, you can implement it numerically, put a set of boundary conditions on it, and get a solution. The ideal cases are diffusion, mechanics, electromagnetostatic problems. You can do electromagnetic waves. These are doable but more challenging. Fluid dynamics can be also solved with finite element. Phase transformations, microstructure evolution, these can be done as well. But you have to have a good handle on the internal stress strain or transformation effects, complex fluid dynamics, electromagnetic waves, vibration problems can be difficult. And we'll hopefully get into more of those effects later.